So the last method that I want to introduce is random forest. And random forest is a very different method from the previous ones. And this is exactly why I have chosen random forest, because it's different, because I want you to get familiar with different species in the realm of, in the land of algorithms, machine learning algorithms. So random forest is an ensemble method. And these are sorts of methods that are based on the idea of combining many simple models in order to obtain a single and potentially very powerful model. So a forest is composed of, if this is one tree, this is another tree, this is another tree, this is another tree. And the naming is exactly from this rationale. So if every single of them is a decision tree, why not combining many decision trees and having a forest? Forest of trees. In this forest, they aggregately can predict something. Isn't it beautiful? This is the idea. So it's a forest because it is composed of combining many decision trees. Random forest is based on two more basic ideas: bootstrapping and forcefully growing different trees. We will see very soon. So the rationale behind random forest, the why part. Random forests and in general ensemble methods are devised to improve the prediction performance. So it's most of time either to improve prediction power or to improve explanation power. Okay, one of them. So random forest is for is trying to achieve, is aspiring for the first goal, prediction power and prediction performance. Like other methods, the why here is a creative idea to address a problem or more than one problem. Which problem? For random forest, low performance of a decision tree on a testing set. But the general idea of random forest can be merged with other nucleus methods as well. So when you learn random forest, you will figure out that the general idea is not tied to the decision tree. Even though random forest is about a decision trees, set of decision trees. But you can use the idea with other methods. So there is this problem with decision trees. There are some drawbacks. The excellent thing about them is their interpretability and explanation power. Power or ability. This is an excellent thing about decision trees. But the other thing is, if we let them grow very large, if we let them grow deeply, let's say, then they memorize rather than learn, then would have low performance on test data set. If we prune them, then they learn, but they would have low performance once again on test. There is another problem with growing very large ones. It is not only the low performance. Let me bring it here. It's not only the low performance, it is also stability. So for one test set, it might score, let's say, 80%. And then for other one, 60%. And then one for 70%. So it's not stable over the sets. If we prune it, it would be stable. It would be, let's say, 70%, 69%, 71%, and so on and so forth. But the performance is low. So random forest is trying to address these problems, to have a stable and high performance at the same time. So let's see how it strives to do so. So the ideas are simple and manifold. Main idea, instead of one single tree, let's have hundreds of trees of the same problem and get prediction values from every single one of them, and then average all the predicted values. So it's called aggregation. Let's change the color. It is called aggregation. So the main idea is aggregation. Instead of one tree, let's have tree 1, tree 2, tree 3, and so on and so forth, and get prediction 1, prediction 2, prediction 3 about one single observation, observation 1, let's say. And then aggregate all of them. Okay, how to aggregate them? Either use a mean for regression problems or use a mode for classification problems. Now the problem is, okay, this is fine, but on one single training data set, if I train different trees, they all would be identical. And therefore, their predictions would be identical. For if you want hundreds of trees, you need to have hundreds of training sets. And that's true. We need to have hundreds of training sets. And we want to use the idea of bootstrapping in order to create those hundreds of training sets. And how? Well, let's assume that this is a training set. Let me write it in a better way. This is a training set, and this is ID. So observation 1, observation 2, observation 3, observation 4. You can have this data set out of it. Observation 1, observation 1, observation 2, observation 3. So it is like sampling with replacement. And we can have another data set. Observation 1, observation 2, observation 2, observation 3, let's say. And we can have another data set. Observation 2, observation 2, observation 2, observation 4. And we can have more and more data sets. So with permutation with replacement, sampling with replacement, we artificially create these data sets from the initial one. So from one data set, we can have many, many new ones. Okay? So you might ask whether the repetition of some of the items would cause a problem, and the answer is no. So if we have more of one item, actually, we are letting the tree of this data set to learn more from the repeated items. So I address the problem of the of not having many training sets. So not only we can have many trees, but we can have many aggregated or bootstrapped, better to say, bootstrapped set 1, bootstrap set 2, bootstrap set 3, and more. And now when we train our trees, because their training data set is different, they would be a little bit different. So two ideas, once again, aggregation of the trees. that requires many data sets, and the problem of many data sets would be solved with bootstrapping idea. And they put bootstrapping and aggregation together and they call it bagging. So what I explained to you is called bagging. So you might ask that whether random forest is a bagging algorithm, right? And the answer is no, it's even cooler than that. It's even more fascinating than bagging. It uses the bagging idea, but there is another problem that it addresses. If we build decision trees on the bootstrap training sets, the decision trees would use the same set of predictors, right? So even though the bootstrapped training sets are different, a little bit different, okay, but the predictors are identical. And the result is composed of very similar, this too, it results on very similar trees. Why they are similar? Because it's always one predictor or two predictors that are very good. They are very good in prediction, and they outperform. They would be chosen by the algorithm as their first as the first steps, first splits on the space, on the feature space. So these predictors, let's say predictor 1 and predictor 2, it is always that they are the chosen predictors by every single tree. So the trees are very similar. Let's give an example. We want to predict income, and we say that income is a function of gender. In the real world, unfortunately, but it is a function of gender. It is a function of a field of study. It is a function of years of education. It's a function of education prestige, whether you have studied in somewhere unknown, on somewhere worldly known, like Russell Group universities or so on and so forth. Years of experience. Okay, let's have all these variables. Okay, even let's not be very picky about gender. We want to put it in the model, and if gender is not a good predictor, it will be omitted by the model. It will be put on the lower side of the variable importance. So let's assume that the field and the years of experience are the most important, the most influential predictors of the outcome. So for every tree, even though the bootstrapped dataset training set is different, these two predictors would be at the top. They will say that, for instance, if field is equal to STEM, and if years is greater than 10, then your salary is over 100k British pound. Okay, and if field is not STEM, and then years are something else, then the result is this thing. So for every tree, these two predictors, they are so good at prediction, they are so closely knitted to the income, that they are always the chosen variables by the tree, no matter the change in the bootstrap datasets. And we don't want it to happen. We want to force our algorithms, our decision trees, to learn from every predictor. Maybe there is something here in education prestige. Maybe there is something here in years of education that we want to capture it. So how to force a decision tree to study, to take all the variables seriously? Well, a simple idea. In every step, we force the decision tree to choose from a subset of the predictors, not all of them. So let's assume instead of leaving the algorithm to choose field and years of experience, let's tell the algorithm that for the first split, you cannot choose field, you cannot choose years of experience, you cannot choose education prestige, you can choose years of education and gender. These are only choices that you have. So then the algorithm is forced to work with these predictors. In other words, the algorithm is forced to learn from these predictors. So this is the trick that changes changes a bagging algorithm to a random forest. So this is another explanation of what is happening. So in every split, the algorithm is forced not to use, let's say we have 47 predictors, not to choose from all 47, but a subset of them. Let's say P2, P7, P14, 23, 33, 35, and 40. So 7 of them. In every step, the algorithm can only choose from randomly a random subset of the predictors, not all of them. So in this way, the decision tree learns from all predictors, and it guarantees that the trees would be different. So once again, these are trees. Let's say this is 1, this is 2, this is 3, this is 4, this is 5. We want many trees, and we want to aggregate the predictions. This is called aggregation. The problem is we need to train every tree on a different training data set, otherwise they would be identical. So we define new training sets out of one initial one. Okay, these are new ones. So this is as 1, this is 2, this is like 3. These are just different. And we call this one the bootstrapping. And the aggregate and bootstrapping together is called bagging. Then we want to force these trees to be different. So different trees. The idea is not letting the trees to choose from all the predictors, but force them to choose from a random subset of the predictors. And then you will have a random forest. So random forests, like decision trees, can deal with both regression and classification problems. And from this perspective, they are amazing. They are ambidextrous. Their performance on test set is better than a decision tree, yet their interpretability is lower. So it's like a trade-off here. We don't have that beautiful tree-like presentation of the results and the relation between predictors and the target. However, we can get something like predictor importance. Which predictor is more important in general? It's a little bit of mitigation of the problem. So we can get predictor importance. Another downside is comparing to a decision tree, random forest has more hyperparameters. It has the hyperparameters of decision trees and a few more. Like how many trees, how many predictors in each split, and even more. But the good thing is they are very, very good at prediction. They are very, very good at it.